Alright, this is section 8.7 in APAB Calc, which we actually do in chapter 2. This is L'Hopital's rule. So we're going to, this last video, I'm going to do a couple of examples. I'm not going to give you P problems, just the E problems. I'm going to finish out a few more of the weirder indeterminate forms that you're slightly less likely to see on an AP. Most of the time the AP presents you pretty straightforward problems. So let's do a 0 to the 0. So if we were to plug into this, right, we'd get sine of 0, which is 0, and we'd get raised to the 0 power, and 0 to the 0 is one of those indeterminate forms. So just like we saw with the 1 to the infinity, the only way to deal with this problem is using that property of natural log. So I'm going to call the answer L. I'm going to take the natural log of both sides, right? So I'm going to take the natural log of both sides. Don't mind my huffing and puffing dog in the background. And I'm going to do that specifically because it affords me the opportunity to drop this number down in front and not have an exponent anymore. So what's going to happen is I'm going to have the natural log of L equals the limit as x approaches 0 from the right of an x, which is really an x over 1. It's relevant because in a second I'm going to flip it. And you've seen this trick already twice in P6 and E6. So when I plug in now, what's going to happen is I'm going to get a 0, right, times essentially something that doesn't exist. Like, so natural log of 0 from the right does exist. It's going to be an infinity. If you picture a natural log graph, it looks like this. So the limit as x approaches 0 from the right, which is, by the way, why there's the plus sign here, of natural log of sine x is definitely negative infinity. So what's going to happen here is I'm going to get a 0 times a negative infinity, which, while it is an indeterminate form, it's not the one I need. It's not division, right? 0 over 0, infinity over infinity. So what I'm going to do is I'm going to flip and make this division, right? So instead of multiplying natural log of sine of x by x over 1, I'm going to divide natural log of sine x by 1 over x. So I'm going to get that this is the natural log of L equals the limit as x approaches 0 from the right of natural log of sine x divided by 1 over x. And now when I plug in, I get something that's infinitely large over something that is also an infinity. If you picture 1 over x, 0 from the right, looks like this. It goes to infinity. So I get infinity over infinity, which means I'm okay to do L'Hopital's, right? So now I'm going to go ahead and do L'Hopital's. When I do my L'Hopital's, it's kind of worth noting that this is an x to the negative first. You might want to go ahead and memorize that this particular thing, when you do the power rule, ends up looking like this. Because it would be a negative 1 x to the negative second, so it looks like you don't have to, but I'm just going to say that it's kind of useful. So I'm going to get that this is the natural log of L equals the limit as x approaches 0 from the right of natural log of sine x. When I differentiate, I'm going to get 1 over the stuff times the derivative of the stuff, right? And on the bottom, I'm going to get this thing, right? Cool. So what ends up happening is I end up getting a cotangent of x over a negative 1 over x squared, and there's still a limit as x approaches 0 from the right. So if you don't want to leave it as a cotangent, actually, you might feel more comfortable. So it is going to be a cotangent, right? But for the record, you can see right away that when you plug in, you get a 1 over 0 and a 1 over 0. That's an infinity over an infinity. So this is still infinity over infinity. So I'm okay to L'Hopital's again. Now, I would point out that there's a slightly easier way to do this L'Hopital's if you're not a huge fan of having this thing on the bottom. If you want, you can simplify this first, because you can recognize that this is actually the limit as x approaches 0 from the right of a 1 over tangent divided by a negative 1 over x squared. So you could make this a little bit nicer. You could do the limit as x approaches 0 from the positive of a negative x squared on top of tangent, which is going to be a little easier to deal with and is still going to give you, so this is going to give you a 0 over 0, so you're also okay to L'Hopital's. So whichever way you choose to go, I'm going to pick this one because I think it's nicer. So I'm going to get that this is, so that my natural log of L, because you don't want to forget that at the end you're going to have to exponentiate, is equal to the derivative of the x squared, which is going to be the negative x squared, which is negative 2x, limit as x approaches 0 from the positive, I've told you we all do this, divided by the derivative of a tangent, which is a secant squared, right? So when I plug in, I get a 0 over a 1, because secant of 0 is 1, so I get a 0 over a 1, my bad, there you go, which means that I get the final answer that the natural log of L is 0. When I exponentiate, L is 1. And that's my answer, right? So again, I know that these are not easy problems by any measure. I don't think you're going to see a ton of problems this difficult, but I wanted to throw them out there so that you've had some experience with them. So we're going to do one more. We'll do an E8. This is going to be the infinity minus infinity example, and then we'll call it a day on L'Hopital's. All right, so last example, infinity minus infinity. So E8, we're going to do an infinity minus an infinity example. Okay, so let's do the limit as x approaches 1 from the right of a 1 over x, 1 over natural log of x. Sometimes I copy the problem wrong. 1 over natural log of x minus a 1 over x minus 1, probably? Yeah, okay. So, when I plug in, I get a 1 over 0 because the natural log of 1 is 0, so 1 over 0, and a 1 over 0, so that's an infinity minus an infinity. So it is indeterminate, but it's not currently written the way I need it to be. Since I have multiple fractions, and in L'Hopital's we usually only have one fraction, the easiest bet is to get a common denominator. So I'm going to go ahead and multiply the first fraction by the x minus 1 over x minus 1, and multiply the second fraction by the natural log of x over the natural log of x. So I'm going to get that this is the limit as x approaches 1 from the right of x minus 1 minus natural log of x, so x minus 1 minus natural log of x, over an x minus 1 times the natural log of x. Well, now when I try to plug in, I get 1 minus 1 minus 0 over 0 times 0, which is totally 0 over 0, so now I'm okay to do L'Hopital's. So when I differentiate, it's up to you. You might want to do this as a product rule on the bottom. The way it is, you might want to distribute and make it an x times natural log of x, which would still be a product rule minus the natural log of x. It's up to you. I'm going to go ahead and leave it as it is. So I'm going to get that my derivative on top is a 1 minus 0, because that's gone, minus 1 over x. And on the bottom, I'm going to get u, which would be this, dv, which is 1 over x, plus v, which is natural log of x, du, which is a 1, right? So I would suggest that you clean this up a little bit. Right now, it still looks like a 0 over 0. It might stay that way. It might not. It's hard to know. So right now, I get, well, let me check if that's true. I get 1 minus 1. Yep, that's a 0 on top. On the bottom, I get a 0 and a 0. Yep, so right now, it's still a 0 over 0, right? So I would suggest it's not a terrible idea to clean this up a little bit. It's kind of up to you how much you want to clean it up, but I think that sometimes when we clean it up, we're going to find that it's a lot nicer than we expect. So I'm going to suggest that the easiest thing to do to start, because I'm not in love with this 1 over x thing, so I'm going to clean up. Okay? I'm going to clean up by multiplying by x over x. And if I do that, what's going to happen on top is I'm going to get, since the limit as x approaches 1 from the right, I'll get an x minus 1. And on the bottom, this x is going to knock out this guy, so I get an x minus 1 plus an x times the natural log of x. Now let's see what happens if we plug in now. When I plug in now, it seems to me that I am still getting so it seems to me that when I plug in now, I get 1 minus 1 on the top, which is still a 0, and 1 minus 1, which is a 0, plus a 1 times a 0, which is still a 0. So so when I plug in, I still get 0 over 0, so let's differentiate again. So I get the limit as x approaches 1 from the right of, when I differentiate the top, I now just get a 1. Well, that's a good sign. And on the bottom, I'm going to get a 1 plus, and then this is a product rule, right? So u dv plus v du. So now when I plug in, right, these guys together are 1. So now when I plug in, I seem to get 1 over 1 plus 1 plus 0, which is a 1/2. And that was a lot of mathing, but there you have it. It's a half. So again, I'm not gonna make you do problems this difficult generally, but I think that it's unfair if I don't try to expose you to some of the more difficult problems that you could see in your math career. I don't really see a logical reason that you would see one this difficult per se. So yeah, so that's it. We're gonna call it a wrap for L'Hopital's.